This is Math 139, and we're looking at section 3.10. We're going to revisit a topic that we discussed earlier, namely exponential modeling. We'll have a chance to review the process of finding the models, but additionally we'll be able to answer some new questions that we would not have been able to answer before our study of logarithms and our ability to solve some additional equations that we've recently acquired. So, we're going to take a look at this problem. We all know it's dangerous to eat perishable food that's been left unrefrigerated. Bacteria multiply extremely quickly at room temperature. In fact, the average time for a bacterium to replicate itself and split into two is 20 minutes. Suppose there are 100 bacteria on a piece of meat left at room temperature. Working by hand, I would like to find an exponential model for the number of bacteria after T hours. One thing that strikes me before I even get into the problem is I do need to be careful with my units here. Notice that the time for the bacteria to split was given in minutes, but my model is supposed to be in hours. So I'll have to be careful with that as I set this up. As you've seen me do before, when I don't have a table, I often like to start by creating one. So let's do that. For a time t in hours, let's let n be the number of bacteria. At the beginning, after no time has passed, we had 100 bacteria. And then every 20 minutes would be a third of an hour, each of these bacteria is going to split and become two. So after 1/3 of an hour, I would have 200 bacteria. And after 2/3 of an hour, they all double again, 400 bacteria. And after 3/3 or 1 full hour, each of these has split one more time, and I now have 800 bacteria. I could keep going, but that'll be plenty for us to work with. All right. In general, my exponential model is y is equal to ab to the x. And in this particular case, I know the a value. We were given the y-intercept, which is 100. So y equals 100, b to the x. Now, we have a couple of options. We can either pick a point and substitute it in, or if we're clever, we might actually be able to figure out the equation here without doing any substituting. I'm going to substitute first, and then we'll go back and kind of talk about the clever way to do this. I don't love working with fractions if I don't have to, so I'm going to choose to plug in this point that does not involve any fractions. Y is 800 when x is 1. Pretty easy to solve, just divide by 100 and 8 is equal to b. Here's what I meant about being clever. Do you remember back a while when we were talking originally about finding exponential functions? And we said that if the x values increase by 1, then the base is the constant multiplier. Notice what happened here. When my x, or really t value here, went up by 1, the number of bacteria was multiplied by 8. So in fact, the fact that the base is 8 should not have really been a surprise to us. All right, whichever way you saw it though, we now have the equation y equals 100 times 8 to the x, or if I rewrite that in terms of my variables, n equals 100 times 8 to the t. All right, the second thing we were supposed to do was talk about the base. The base is 8. And we can interpret that a couple of different ways. We could simply say that every 1 hour, the number of bacteria are multiplied by 8. Or if we want to be mathematically a little bit fancy, we can use the technique that we used before. And it's been a little while since we've talked about this, so let me remind you. What we did was took our base and essentially multiplied it by 100%. 8 would be 800%. Then we subtract the 100% that we started with. So in this case, we could say we have a 700% increase in bacteria every hour. So really just two ways of saying the same thing. All right, the last question. At this rate, how long would it take our 100 bacteria to grow to 1 million bacteria? This is the question that we would not have been able to answer with what we knew the last time we did exponential modeling. So thinking about my equation, n equals 100 times 8 to the t, I'd like to know how long it's going to take for there to be 1 million bacteria. So my n is 1 million. Since this particular problem asked us to solve by hand, I'll go ahead and say I need to isolate my exponential. I need to get that 8 to the t by itself. So I will divide by 100. That gives me 10,000 equals 8 to the t. And then it's your choice. You can use either method 1 or method 2 for solving this. I'm going to go ahead and just say the inverse of exponential base 8 would be a log base 8. So the log base 8 on both sides. Math menu and down to that log base. Is about 4.43. And of course on the other side, the exponential and the log base 8 are inverses, so I just have the t left. So it takes a little less than 4.5 hours for our 100 bacteria to become 1 million bacteria. All right, let's try another one. Once again, we've seen problems like this before. We're just going to answer a new question. The nuclear disaster at Chernobyl, Ukraine in 1986 released a large amount of radioactive material into the environment. One of the most dangerous was cesium-137, with a half-life of 30 years. This time we're being asked to do our modeling using regression and find an exponential model for the amount of cesium-137 T years after 1986. So I'm going to employ my usual technique here. I'm going to make a table. T will be years after 1986. And let's see here. P is going to be the percent of our cesium-137 that still remains. At the beginning, time 0, which was 1986 when the disaster occurred, 100% of what was released is still there. Now the half-life is 30 years. So after 30 years, the percentage would be cut in half. We're now down to 50%. That's really enough, but I'm going to write just maybe 1 or 2 more lines. After another 30 years, so it's times 60 years, it would cut in half again to be 25%, and so on. All right, we're going to use regression this time. So in my stat menu, I'll edit, and I'll put in my values. And then back to the stat menu, and I'm going to calculate. And it specifically says an exponential model, but half-life problems always are. So I'll do exponential regression. And let's see, everything looks good there. We'll just calculate. A is 100, not surprisingly. That was the y-intercept. We saw it right there. Our b is about 0.977, and we have a perfect correlation coefficient here. R squared is 1. So I'm going to write P equals, because my y is really the percent, A was 100, times our B, I'm going to round that off to 0.97716, to the x, but our x is actually t. Keeping more decimal places in the base is always a good thing. I think we talked about that a little bit before. A little bit of round-off error in the base can make some fairly large round-off errors as you go forward. So there is the model, the exponential model for the amount of cesium, or the percent. I guess I said amount, it really is percent, of cesium-137 that remains. The base of my model is this 0.977 approximately. Just to talk about it, I'll round it off. And if I change that to a percent, 97.7%, subtract off the 100% that we start with, and we get negative 2.3%. So the amount of cesium-137 is reduced by 2.3% each year. Decreases by 2.3% each year. All right, finally, how long will it take for the amount of radioactive cesium-137 left in the environment to be only 10% of the amount released? So I go to my equation, P equals 100 times 0.97716 to the t, and I want the percent to be 10. So I'm going to put 10 in for P. All right, to solve that equation, I need to get this exponential by itself, so I'll divide by 100. I get 0.1. And then I need to take the logarithm. I can either take the inverse, the logarithm of base 0.97716, or I can use the properties. I guess I was using the inverse last time, so I'll be consistent. Looks a little weird because it's a weird base, but that's okay. We chose it, of course, because it is the inverse of the exponential. So that's going to give me t. And if I go ahead to my calculator and do my log base, 0.97716 of 0.1, I get 99.66. So just under 100 years is what it's going to take to get down to 10%. There will be 10% of this cesium-137 left. All right, we will pause there and do the rest of it in section B.